instrument that we actually use that is tempered. Our voices, we hopefully we are using pure tuning with voices, and with our instruments, we hope we are using pure tuning. And I guess I shouldn't say only one instrument. The piano and also the mallet instruments, the marimbas, the xylophones, bells, all of those have to be tempered too. The reason we have to use tempered tuning with the piano and with those is because we have to be able to make G sharp and A flat be the same pitch. Okay? Otherwise, this piano would have to be 6 more feet long out that way, because in real truth, G sharp and A flat are not the same. Okay? When you sing a G sharp in the key of E, you are actually, without anybody telling you, just because you have good musical knowledge and understanding, you're singing a G sharp that is a little higher than on the piano. And that's why many of the good choirs prefer to sing a cappella, because technically the piano is a little bit out of tune. And when we are in the key of E major, we want that G sharp to be really tall. But we're in the key, when we're in the key of D flat major, we want that A flat, which has to be the same note as the G sharp on the piano. We want it to be really flat. Okay? And if we sing it absolutely in tune and then go check the piano and touch that A flat, it won't be quite in tune. All right? Now, that means we have to forever wander around in 2 different languages. Okay? For instance, when we are composing, when we are writing our own songs, if we're in the key of E major, we have to make sure that we write the G sharp. All right? There is no A flat in the key of E major. Although sometimes we are tempted to write the A flat, because sometimes brass players read A flat better than they do read G sharp. But even with that temptation, we have to say, no, we've got to make sure we use the G sharp, because that's actually a different pitch in the key of E than the A flat is. Okay? However, we also have to be able to talk enharmonics. That's a big word that you're going to learn in about 3 chapters. Enharmonics means we technically have 2 names for the same note. Okay? But remember that whenever we talk about enharmonics and 2 names for the same note, we're talking in tempered tuning. We'll never ever talk about enharmonics when we're talking about pure tuning, because G sharp and A flat aren't the same. Right? But in the piano language, G sharp and A flat are the same. All right. So I needed to clear that up. Another thing I didn't really clear up for you, and I know you just hate to get physics lessons. How many are taking physics right now? And you just hate it, don't you?
I love it.
No,
Good
this is
for you
nice
guys.
class.
I hated it. Sorry, I hated it so bad. It could have been the teacher. I don't know. But
Yeah,
it
yeah.
had to have been the teacher. What am I saying?
Momolo's awesome.
Well,
Really, I don't
Momolo
know
probably
why.
wasn't born when I took physics. But anyway, let me give you a really rough, and if you really want the honest-to-God truth about the physical acoustics, you should probably ask Mr. Momolo. But I'm going to give you a really rough drawing. Let's pretend this is Philip's, straight as a string, isn't it? Let's pretend that's Philip's new mandolin A string. And it's supposed to be straight, by the way, only I can't draw a straight line. When he plucks that A string, it begins to vibrate. It first goes this way, whichever angle he moved his fingers to start it. And that string actually bends out kind of like that. And then it comes back almost as far, but it can't go clear as far, because if it went as far, then it would never stop, right? It has to lose something each time. So it comes over to this side almost as far. Then it comes back to this side again almost as far. But again, it can't be as far or it will never stop. But it just keeps going back and forth until it finally stops. through the use of magical machines that can actually count the number of cycles that goes back and forth, we can find out that Philip's A string, when he plucks that, is gonna go back and forth 440 times per second. That's why it's just a blur. I mean, that's, and in fact, on an A string, you probably can't even see it moving. If you go down, say, to the string base and you pluck the lowest string, you can actually see it going back and forth because it's going so slow you can see it. But everything else, and if you opened up a piano and hit an A 440, it wouldn't look like it's moving at all. It really is, but it's moving so fast you can't see it. All right? But supposedly, and I shouldn't say supposedly because it's true, if you are in tune nowadays on your A, they say it cycles 440 times per second. That means, and it just so happens that the A an octave lower, that's the A we're talking about right there in treble clef.
220.
This A down here is actually, I think it's 220, am I right? Okay. All right, and that gives you some mathematical hint as to how it works octave-wise. If you've ever heard anybody who sets up PA systems, like you, for instance, setting up PA systems, or if you've ever set up a PA system and you hear a 60-cycle hum, people will refer to that as, oh, I hear a 60-cycle hum. I believe that means you've got a bad ground wire somewhere. But 60-cycle means that is way down here. Is this piano on?
Yeah.
It is. Or, yeah, it's right there. That is so low that that string would only go 60 times per second. And so if you hear that sound, you know you have to replace it. Yeah. Okay, so frequency and cycle are kind of the same words, one way or another. Now, another interesting fact that you might find fun to discuss, the sense of pitch of humans over the years has not always been the same. They estimate that in Mozart's time, A was really only 425. Which is about where we would guess A flat would be right now. It might even be a little bit lower than our A flat. The reason may have been, and the historians only speculate on this because nobody wrote much about it, but the reason was that they had not developed a metal wrap for their stringed instruments. The gut strings that they had on their violins, violas, and cellos were actually, they looked like they came right out of the sheep. I mean, it was, or the cat, whatever. I mean, they were gut only. And they were very brittle, and if they had been tuning them up to 440 at that time, they would have been replacing them 3 or 4 times a day, because they would just break. But 425 is not as high a pitch, so it's not as tight of a string, and that way they didn't have to replace them all the time. That also felt comfortable to them at that time. Somewhere around I'm going to say 1910, they began to, and I could be wrong on that, I'm just guessing, I think it was at the turn of the century somewhere, they began to develop the silver wrap that went around the gut string, and it made the gut string much more solid. And ever since then, we have been raising what we think the pitch for an A should be until, actually, as I tell you now, A is 440. That's actually kind of a lie. If you go to any of the major professional orchestras, symphonies, like the Chicago Symphony or the New York Symphony, and you bring in your little strobocon, which is that measures frequencies, and you listen to the oboe player play that A, it's probably 446 or 447 by now. And partly, do we have any string players in here? Just it used to be as all. And mandolin, there we go. Partly it's stringed instrument people that are at fault because the tighter the string, the more brilliant the sound. And so, concert masters will often reject the oboe player's first offering of an A. The oboe player will actually try to give you an A440, and they tap the little tuning fork and listen to it and they play. And then the concert master says, no, we want it higher than that. And so a lot of them are 446, 447, but it makes it sound a lot more brilliant when the strings play. Someday it may be 450. If they get much higher than 450, they're going to have to figure out how to get titanium strings, I think, because at 450, I'm afraid the E strings would just pop because they're so thin a string anyway. Okay, now, that sort of fills in the gap of why we had to talk about pure tuning and tempered tuning. You may have had